Is about the open source robot operating system, or ROS. And a very important resource throughout the class is going to be the ROS webpage, which I'm linking to here. And let's also quickly check it out. This is where you'll find a lot of very important information. In particular, the ROS wiki is the starting point for tutorials and documentation. So you'll be making heavy use of that. But the website is also a good starting point for a very important question. What is ROS? What actually do we have there? And we can take a look at this, and it's obviously an important enough question that they attempt to answer it directly on the website. And what they tell us is that ROS is a collection of tools, libraries, and conventions. And in particular, ROS is a collection of software for robotics, but it's actually more than that. So fundamentally, you can think of it as a collection of software, but there are other components as well. And here, what they also tell us is that ROS is plumbing, tools, capabilities, and ecosystem. So let's take a look at that one by one. So before we actually get further into detail in this, let's take a quick look at ROS in action. And the first thing that I want to mention is that ROS does not replace your computer operating system. Even though it's called the robot operating system, it doesn't replace the operating system that's running on your computer. ROS is a collection of software that runs on top of the operating system you are running on your computer. Usually, that will be Ubuntu Linux, which is what I'm running on my computer right here. ROS does support a couple of other OSs as well, but usually you will be running Ubuntu Linux on your computer if you're going to use ROS. And what I'm going to do here is I have ROS installed. So I'm just going to fire up a terminal. And what ROS does is it organizes code for you. It has this notion of a workspace. You can have multiple ROS workspaces. Here I have 2 of them, and I'm going to use one today, our ROS demo workspace. And then one thing you can see is that ROS gives you a way to organize your code, organize the software that you have for robots. And in particular, if I go into my source folder, here I have 2 packages. So the first thing that ROS does for you, it gives you a way to organize your code. And all of this quick live look at ROS, you can watch this bit now. You probably want to watch it again after you've gone through the ROS tutorials, and then a lot of these concepts will be even more clear. But the first thing that ROS does for you, as I said, is gives you a way to organize your software, and in particular into these entities called packages. Then the next thing that I'm going to do is actually run some code. And many of these steps will be very clear once you've gone through the ROS tutorials. So I go ahead and launch some code. ROS gives you a way to not only organize your software, but also compile it and run it. Here, my code is already compiled, but part of the tutorials will be showing you how to compile your code through ROS. And now, what I'm going to do is, once I have my robot running, I am going to start the robot visualizer, or RViz, which is one of the very important tools that ROS provides to you. And this visualizer actually is going to show me what's happening here. And this particular piece of code that I'm running is a simulated robot that's just moving around in space. And RViz, the robot visualizer, which is what you see here, is a tool provided through ROS that allows you to do exactly that, visualization for many, many robot-related tasks. And in this particular case, RViz is showing us the pose of this arm as it's moving through space. And a lot of what we're going to do in the class is the fundamentals of this. How do you actually compute the pose of the robot? But here we have, through ROS, a way to visualize this kind of information. Now you're getting a sense for some of the things that are listed here, right? Why ROS is more than just, software. So ROS is plumbing. It gives you a way to organize and a way to manage your code. But also, very importantly, it provides communication between multiple pieces of code that are all running. And it turns out that robotics is a very distributed endeavor, if you wish. Whenever you have a robotic system has many, many components, and all of those components end up having to talk to each other, right? So it's easy to think about a robot as just one entity, but what actually happens in real life is that a robot is made up of lots of individual components in hardware, and you can think about that in software as well. So, for example, let's say you have a robot that is navigating around, and it is equipped with a couple of sensors, right? Let's say one of the sensors is a laser rangefinder. So in that case, what might happen is the laser rangefinder might have a driver that's running and that is giving you the data as seen by the laser rangefinder. So this will be what's called a ROS node. Then let's say you have a piece of software that does what's called localization. We'll get into the details of it later in the class. But localization, as the name implies, it's a piece of software that, based on the data from the laser rangefinder, tries to compute where the robot is located in space, right? So let's say you have your localization piece of code. Okay, so this is another ROS node that's running. And obviously, in order to do localization, you will need the data from the laser rangefinder. So somehow this data needs to go from the rangefinder to the localization node, right? What the localization does, it tells you where the robot is, right? But that's not all of it. Let's say, the robot has a goal. It needs to get somewhere on a map, right? And there's a piece of software that, if it knows where the robot is and it knows where the robot needs to go, it can compute the path to get from the start to the goal, right? And let's say that piece of software, let's call it the path planner. This is another node that's running, and this node needs to know where the robot is, which is what the localizer produces. So somehow that data needs to find its way from the localizer to the path planner, right? Also, the path planner needs a goal. Somebody needs to tell it, hey, this is where the robot should go. So somehow a command needs to come to the path planner. Okay, and let's say we don't really know who's issuing the command. Maybe this is a user that's clicking a point on a map. Then the path planner computes a path. This is how the robot needs to drive to get to the goal. How does that eventually happen? How does that physically happen? Well, commands need to be sent to the motors that are turning the wheels of the robots, right? Let's say the robot has 4 wheels. Each wheel has its own independent motor, and of course I'm simplifying, right? So then we're going to have 4 motor drivers. Okay, and then the path planner, once it's computed a path, that path needs to be executed, so this will be sending commands to the motor drivers, which will actually be turning the motors, right? And this is just a very simple example. In practice, any robot that does a non-trivial task, this graph of components is going to be huge. And on the ROS webpage, you'll actually see examples of graphs like this. And what's interesting here is that, right, this is a communication graph. There are all different kinds of data that are flowing, right? So for example, the laser driver, so the laser rangefinder, the driver that's running the laser rangefinder to the localization, this is going to be laser data. Okay? The localizer outputs robot location. Okay? This entity, which we haven't really bothered ourselves with too much, tells you what the goal is. Okay? The path planner computes the path, and what it actually sends to the drivers, to the motor drivers, are motor commands. Okay? So all of these are different data types, different kinds of streams. Some require a lot of bandwidth, some not so much. Some, you'll have a lot of data flowing. Some you'll get every now and then some information, right? Maybe, for example, the robot also has a camera, and it's using not just the laser rangefinder, but also the camera as input to the localization, right? And in this case here, let's say, for example, it's a VGA image that's coming through. It could be a different resolution, but let's say in this particular case it's VGA, right? The point I want to make here is that robotics is building a robot system is a very distributed task with lots and lots of components. A lot of modularity is important, and there's a lot of communication between all of these components. So what ROS does, it gives you a way to manage the code for all of these components, to manage it, to organize it, to compile it, to run it. Once all of these nodes are up and running, so you've written your code, you've compiled it, you've run it, ROS provides all of these communication channels. So this is something else when they say that ROS gives you plumbing, communication between components. And that is a critical aspect in robotics precisely because of the very distributed nature of the task. So what happens in ROS uses what is commonly referred to as the publish-subscribe model. Which is often shortened as just pub-sub. People will say pub-sub. So what happens is one particular node can say, I'm going to publish this kind of information to the rest of the world. The laser driver says, I publish laser data. I don't really care who's listening and who needs it, but I'm just going to publish it, and anybody who needs it should just subscribe to my feed. So then the localization node will say, okay, I'm going to subscribe to laser data, and I'm going to subscribe to the image data from the camera, and in turn, I'm going to publish robot location. So this kind of publish-subscribe predates ROS. It's a model that's much, much older and used in many other software frameworks. It is heavily used by ROS, and ROS gives you this ability for components to communicate between each other. Some of the things that are particularly nice in ROS is that,